friends, welcome to today's video in our binary tree series. I'm Chinyel, I'm a software engineer at Microsoft in Dublin, Ireland. Today we'll be learning how to traverse a binary tree using the depth first search approach. As you may already know, mastering tree traversal is the key for acing binary tree interview questions. So without any further ado, let's get right into it. The depth first search approach of binary tree traversal is divided into three: the pre-order traversal, the in-order traversal, and the post-order traversal. I will use the concept of a binary search tree to give you an explanation that will stick forever. Talking about binary search trees, if you have not watched our video on binary search trees, you should do so because it is important for your coding interviewing skills. So back to business. Recall that a binary search tree has the following properties. The left subtree of a node contains only nodes with values lesser than the node's value. The right subtree of a node contains only nodes with values greater than the node's value. The left subtree and the right subtree each must also be a binary search tree. So I will summarize by saying that the left subtree is less than the root node and the root node is less than the right subtree. So you can take this to be the flow of in-order traversal, which typically means that in in-order traversal, you first visit the left node and then the root node and finally the right node. A tip you can use to remember this flow is that just like the name in order, it is in order because it follows the same flow as the binary search tree. Another thing to remember here is that the root node is at the center, that is, between the left and the right node. In the pre-order traversal, the root node comes first, just like the prefix pre suggests. So you first visit the root node, then the left node, and finally the right node. Finally, in a post-order traversal, the root comes last, just like the prefix post suggests. So you first visit the left node, then the right node, and finally the root node. This is what an algorithm for a pre-order traversal would look like. So we first print the value of the node and then call the same print function on the left node if it exists and then on the right node if it exists. An algorithm for an in-order traversal will look like this. We call the print function on the left node if it exists, print the value of the node, and then call the print function on the right node if it exists. Finally, the algorithm for post-order traversal will look like this. We call the print function on the left node if it exists, and call it on the right node if it exists, and finally we print the value of the node. Observe how the three algorithms are almost the same. The only difference is in the position where we print the node. And this position also follows the prefix. In pre-order traversal, the node is printed first before the recursive call on the left and the right nodes. In the in-order traversal, the node is printed at the center, that is, in between the recursive call on the left and the right nodes. Finally, in the post-order traversal, the node is printed last after the recursive call on the left and the right nodes. Now, using this tree as an example, let's see how these three binary tree traversal algorithms will print out the node's value of this tree. By the way, if you have not seen our video on level order traversal, hurry and watch it. Back to business. So, for the pre-order traversal, the function starts with the root node, which is node A. So we print node A and call the function on the left child if it exists. The left child exists and it is node B. So we print node B, call the function on the left child of node B if it exists. Node B has no left child, so we move to call the function on the right child of node B if it exists. But node B has no right child as well, so we move to call the function on the right child of node A if it exists. The right child of node A is node C, so we print the value of node C and call the same function on its left child if it exists. The left child of node C is node D, so we print node D and call the function on the left and right child of node D if they exist. But node D has no children, so we call the function on the right node of node C if it exists. But then again, it doesn't exist. Now watch how these nodes were printed. We first printed out the root node, node A, then the left node, node B, and then the right node, node C, and finally node D. Let's see how Inorder traversal will print the nodes of this same tree. We also begin with the root node A. We call the function on the left child of node A if it exists. The left child of node A is B, so we call the function on the left child of node B if it exists. Node B has no left child, so we move on to print node B and call this function on its right child if it exists. Node B has no right child, so we move on to print node A and then call the function on the right child of node A if it exists. The right child of node A is node C, so we call this function on the left child of node C if it exists. The left child of node C is node D, and calling the function on this node calls the same function on its left child if it exists. But node D has no left child, so we move on to print node D and call the same function on its right child if it exists. But node D has no right child, so we move on to print node C and call this same function on its right child if it exists. But node C has no right child. Now, notice how the Inorder traversal printed the nodes. It started with printing out node B, which is the left child of the root node, and then it printed the root node, and then it printed the left child of node C, which is node D, and finally node C. So now let's look at how Postorder traversal will print the nodes of the same tree. As usual, we start with the root node and call the function on its left child if it exists. The left child of the root node is node B. Calling the function on node B calls the function on its left child if it exists, and node B has no left child. So we proceed to call the function on the right child of node B if it exists. But then again, it does not exist. So we print out the value of node B and move on to call the function on the right child of the root node, which is node C. So calling this function on node C calls the same function on its left child if it exists. The left child of node C is node D. So calling this function on node D calls the same function on the left child of node D if it exists. But node D has no left child. Then we call the function on the right child of node D if it exists. But node D has no right child as well, so we move on to print node D and call the function on the right child of node C if it exists. But node C has no right child, so we move on to print node C and then print node A. So we can see that the Postorder traversal printed the nodes in this way. First, it printed node B, which is the left child of the root node. Then it printed the left child of node C, which is node D. And then it's printed node C. And finally, it's printed node A. The time complexity of all these algorithms will give you O of n, where n is the number of nodes. This is because all the nodes are visited exactly once. All right. Thank you for watching until this point. If this video was helpful, please give it a thumbs up and hit the subscribe button to see more videos like this in the future. Thanks again and see you in my next video. Bye!